All right, so here we are in section 2, which deals with discrete probability distributions and a very special one, which is a binomial probability distribution. So the key concept here is just to be able to identify the binomial probability distribution, which is a special case. And the special cases, there are only two outcomes, hence binomial, okay, two outcomes. What we're going to be able to do is we're going to be able to describe the binomial probability distribution, and then compute the mean, standard deviation, and significantly high, significantly low values for the binomial probability distribution. Is just another formula. In fact, chapter 5 in and of itself is just a bunch of formulas, and it's kind of going to be like this from now until the very end of the semester. You're just going to know what formula you're going to use and why you're going to use it, okay? So without further ado, let's just go ahead and start reading some of this stuff. So the binomial probability distribution allows us to deal with circumstances in which the outcomes belong to two categories, either heads or tails, on or off, yes or no, survived or died, okay? Now, there are criteria that we have to meet. And the first one is you got to have a fixed number of trials. The second criteria, each trial must be independent. And we should remember what that means from chapter 4. But if not, remember, the probability of one event occurring does not influence the probability of another event occurring. So each trial must be independent. 3, each trial must have an equal chance of occurring. So, for example, if you take a coin and you flip it, heads or tails, and then you take that same coin and you flip it again, your outcomes do not, or the chance of you getting a heads do not change, and the outcomes do not change. And then the fourth, outcomes are classified as success or fail. You either get a heads or you don't. You either answer yes to the question or you don't. If you skydive, you're either going to survive or die. Like, that's it. 2 outcomes, okay? Now for a bunch of notation, because the formula that we're going to be using just has a bunch of letters in it. It's not difficult at all, but let's just go ahead and let's define this. So the letter S is going to stand for success. F stands for fail. P of S equals the probability of success. P of F is the probability of failure. And just remember, P of F is equal to 1 minus the probability of success. They're complements of each other. N is going to be the number of trials. X will be the number of successes. And then P of X is going to equal the probability of getting exactly X successes among N trials. Okay, so we're going to look at a pretty easy example here. So when a adult is randomly selected, that's a typo. This is supposed to be when an adult is randomly selected with replacement, there is a 0.85 probability that that person knows what Twitter is. Suppose that we want to find the probability that exactly 3 of the 5 randomly selected adults know what Twitter is. Part A, does this procedure result in a binomial probability? Well, let's just walk down through them. First, fixed number of trials. Well, in this case, there are 5, sorry, I wrote 3. There are 5 randomly selected adults. So yes, we have a fixed number of trials. Second, all the trials are independent. Now, how do we know this? Well, you are randomly selecting 3 of them, and you're asking them one question. Do you know what Twitter is? The answer of one adult will not influence the answer of another adult. And if you think about it, the way that you're asking the question, do you know what Twitter is? The outcomes will be either yes, they know Twitter, or no, they do not know Twitter. And then the last one, we know what the probability of success here is. There is a 0.85% chance that that person knows what Twitter is. So probability of success is given. And is equal to 0.85. So answering question A, does this procedure result in a binomial probability? The answer is yes. So if this procedure does result in a binomial distribution, which it does, identify the values of n, x, p, and q. Okay? So n is going to equal 5 because we have 5 adults. X will equal 3 because we are randomly selecting 3 of them. P is going to be the probability of success. So that's going to be 0.85. And now Q is going to be that probability that they don't know what it is. So Q is going to equal 1 minus P, or Q equals 1 minus 0.85. So Q is going to be 0.15. So maybe I need to define that up above. So let's scroll back up above. Actually, I'll just write it right here. Also written as Q equals 1 minus P. Okay? So now that we have that defined. All right, perfect. So using the binomial probability formula. Okay? So I'm going to give us the formula, and then I'm going to show you how to use it. So our formula is P of X is going to equal n factorial over n minus x factorial times x factorial multiplied by p to the x multiplied by q to the n minus x for x equal to 0, 1, 2, all the way up to however many values you have. Okay? All right, so here's the formula, but I think it's really important that we understand where this formula comes from. So I'm going to show you how we actually derive this formula. Your book does not show this at all. So this is just straight up math, and here's how we came about this formula. So let's consider this situation. And I think we've all been here before. You walk into a room and it's dark. Okay? And normally, and I see this all the time in teaching, all right? So you walk into a dark room, and there are 2 light switches. Okay? And with the switches are either going to be on or off. The probability of a student turning on the lights is 0.30. All right? using this information, derive the binomial probability formula. All right, so here's what we got. You walk into a room, it's dark, there's 2 light switches. We know the probability that a student will turn on a light switch is 0.3, but the question becomes, how many different ways can that occur? Okay? So if you think about this, we're going to let x equal the switches turned on. Okay? So if we think about this, and off to the right here, off to the right, I'm going to go ahead and just, this is, I'm going to draw like a little table here. So switch 1, switch 2. We can have the situation where both switches are turned off. We can have the situation where one switch is on, the first or the second one is off. The third situation, first switch is off, second switch is on, and then the last situation, both switches are on. This should look extremely familiar to us because this is the same thing as flipping 2 coins. You're either going to get heads or tails. So it's the same exact setup here. So if I were to break this down, we would basically have 0, 1, 2, 0, 1, and 2 ways that this can happen. Okay? So we're going to build off that knowledge right here. So when we come back over to here, x equals the switches turned on. Well, we can have 0 switches on, we can have 1 switch on, and we can have 2 switches on. Okay? Now we got to worry about, well, how many ways can that occur? Well, since order doesn't matter here, we're going to look at a combination. In other words, 0, sorry, wrong one. We have 2 light switches. So this is going to be 2 choose 0 light switches. Okay? And that should equal 1 if we go ahead and calculate that. Now for the next situation, we can have 1 switch on, 1 switch off for the first case, or the second case, first switch off, second switch on. So this is going to be 2 choose 1 or 2 possible outcomes. And then with the third situation, this is going to be 2 choose 2, or how many different ways can you have 2 light switches and you have both of those switches on? And that only occurs one way. So notice here, and I'm going to highlight here for us so you can see. That's what this represents right here. Okay, so we're using our counting techniques from chapter 4 to figure out how many ways can these light switches be turned on. Now, the next thing we got to worry about is going to be this P of X and Q to the N minus X thing. Well, if we think about this, and I'm going to write this out here. For the very first situation where no light switches are off, we know that the probability that a student turning the lights on is 0.30, which means the probability that they will not turn it on is going to be 0.70. So if we really think about this, we have 2 light switches. Here's the first switch. There's the second switch. Okay? So that's going to be 0.70 times 0.70. Now, let me kind of extend this out here a little bit. This is going to be 0.70 to the second power because you have 2 of them. Now, I'm going to do this for the next 2 rows, and then I'm going to kind of work with the numbers here a little bit, and you're going to see how this actually just magically appears. So for the second case, we have 0.30 times 0.70. In other words, one of the switches is going to be turned off, and the other switch will be turned off. And here's the beautiful part about this. We know that it can occur 2 different ways. The first switch on, the second switch off, or the first switch off, the second switch on. So I'm going to multiply this by 2. Now that you can see that I multiply this by 2, in reality, I can go back to the first and multiply this by 1 because there's only one way that both light switches can be off. And then for the last part, there's only one way that both light switches can be turned on, and the probability for each switch being turned on is going to be 0.30 for each of them. So we have 2 times 0.30 times 0.70 for our second row, and then 0.30 to the second power. Now, I'm going to write in red something that hopefully makes sense, all right? And I'm going to explain it, but I'm going to write this right here. Let me put this one in the back. Give myself a little bit more room here. All right. So I just wrote those in red because I want to really drive home a point, okay? In the formula, we have p to the x and then q to the n minus x, okay? So if we let x equal 0, then what we're saying is we don't want any light switches turned on. So the probability of no light switches turned on, and I'm going to get my highlighter out here, so is going to be 0. In other words, 0.3 to the 0 power, because no light switches are turned on. And now, if you look at the exponent of the number 2 on the 0.70, well, that's really n minus x, or 2 minus 0, meaning 2 light switches are off, none of them are on. So for the next row, okay, you have at least, or I'm sorry, I don't want to say at least, you have exactly 1 light switch turned on. So x is 1, and then 0.70, that's going to be the number of light switches minus 1, or 1. So that's how we get that. And then for the very last row, you have 2 light switches on. So that's going to be 0.3 to the second power times 0.7 to the 0 power. And hopefully now you can see just how we derive this binomial probability formula. And it's because we are creating a binomial probability distribution. And then we're looking at the probabilities associated with each outcome. So over here on the right-hand side, if I were just to multiply these out, I can go ahead and do that real quickly. So for the first one, we're going to get 0.49. For the second row, we're going to get 2 times 0.3 times 0.7, or 0.42. And then for the last situation here, we're going to have 0.30 to the second power, which is 0.09. So now I want you to think about a time when you walked into a classroom and there were already people inside, and it was early in the morning, and there were like, I don't know, let's say 5 students, and the lights were still turned off. Well, it makes sense because normally people don't want to turn on a light. However, I would hopefully expect either 0 lights or at least one of the lights is turned on, but very few students turn on both lights. And that's why when you're sitting in the classroom early in the morning, the professor always walks in and turns on at least one light because they're either both off or one of them is off. And then the professor usually says, well, if you walked in, you should have just turned on the lights. But anyways, let's kind of just look at this again. All right. So we created our binomial probability distribution. We looked at the number of ways each can occur. We found our probability of success raised to the x power, the probability of failure raised to the n minus x power, and then each one of these on the right-hand side basically just generated the probabilities that we wanted. So P of 0 is going to be 0.49, P of 1 is 0.42, and then P of 2 is 0.09. So you know what I want to do? Because using the mean and standard deviation, I'm going to do that. I think I want to do an example real fast, just to show you how everything works. Okay, so here's an example right here, and I'm going to just walk us through everything on how to do all this stuff. So if you need to, pause the video, write down the question, and then what we can do here is we'll just do this. We'll walk through it together. So standard tests such as the SAT, the ACT, the MCATs, whatever have you. Typically, they use multiple choice questions. each with 5 possible outcomes. So A, B, C, D, and E. Now, of those outcomes, one of them is correct. So assume you guess on the next 5 questions. What we're going to do here is this. We're going to create our binomial probability distribution table using that binomial probability formula. And then we're going to answer the following questions. The probability that you get exactly 3 questions right, or the probability that you get less than 3 questions correct, or the probability of getting at most 2 correct, and then the probability of getting none correct. So the first thing I want to do is create a table, all right? So part A, we're going to create this table, and I'm going to let x equal the number correct. Okay? So we can get the situation where we have 0 correct, 1 correct, 2 correct, 3 correct, 4. And if you're really lucky, you can get all 5 correct. Now, on the right-hand side of this table is going to be our probability formula, binomial probability formula, which is P of x equals NCR times P to the x times Q to the N minus x. Okay? So for this very first one here, we're going to find the probability of getting none of the questions correct. So you guess on the next 5 questions and you don't get any of them correct. So to demonstrate that, I'm going to write out the formula. So we have P of 0 is going to equal, we have 5 questions and we're choosing, oh, sorry, I put an N up here. It's supposed to be an X, my bad. I do that all the time. So we have 5 questions. We're choosing to get 0 correct. Now the probability of getting a question correct, well, if you think about it, you have probability of success is going to equal 1 answer is correct out of 5 possible choices. So that's going to be 0.2. So this will be 0.2 to the 0 power times the probability of failure, which is 1 minus the probability of success, or 0.8 to the 5 minus 0 power. And when you do the math, you're going to go ahead and get 0.32768. So basically a 33% chance of getting none of them correct. All right? So now we're just going to replicate this formula. I'm going to write out the next one here, but after this, I don't think I'm going to write any of them out because it's just a bunch of writing. But for the next one, the probability of getting 1 correct is going to be 5. Choose 1 correct times the probability of 0.2 raised to the first power and then 0.8 raised to the 5 minus 1 power. Now, if you're using a calculator like a TI, 80, whatever, you're going to want to make sure that you just type everything correctly. So let me show you how to do that on a calculator here. So there's my Dragon Ball Z stuff. I'm a huge fan of Dragon Ball Z. Here's my calculator. All right. So on my calculator, now if you got a different one, you just got to let me know and I can find a video, or you could just look one up yourself. But I'm going to clear this out. So we're going to do 5, choose 1. So I hit 5, the math button, go over to probability. There's my NCR right here, option 3. So it's going to be 5, choose 1 times 0.2. So I put it in parentheses, 0.2 raised to the first power, end the parenthesis, and then times parenthesis 0.8 raised to the 5 minus 1 power, end the parenthesis. And then when you hit enter, we come up with the wrong answer, of course. Oh, I'm sorry. This is the right answer. This is 1. I was thinking I'm doing 0. Anyways, so we got 0.4096. So I can go back into our notes here. 0.4096. I hate it when I'm thinking one thing, but then I see another thing, and I'm like, oh, great. But anyways, just repeat this process for every single one of these. So P of 2 is going to equal 0.24 or 0.2048. P of 3 is going to equal 0.0512. The probability of getting exactly 4 correct 0.0064. And then if you guessed on every single problem and you got every single problem correct, the probability of that actually occurring is 0.00032, which, if you really think about this, it should make sense. I mean, think about not having any idea what the next 5 questions are, and you were just guessing A, B, C, D, or E, and you got it right for every single one. The chances of that happening are almost zero. And if you look at our table, it's exactly what's happening here. Okay? So I guess what I can do here is just to condense this to make it look nice again. X equals number correct. Because to be honest with you, this is how you would probably find it if you're reading an article or something like that. So X equals number correct. This is going to be P of X. 0, 1, 2, 3, 4, and 5. All right, and then I'm just going to write out the probabilities here. 0.32768, 0.4096, 0.2048, 0.0512, 0.0064, and then the last one is going to be 0.00032. Awesome. So part A is done. We got our table. This is exactly what it is. If you wanted to, you can create a binomial probability distribution graph where you would just have a bar graph and you would actually just measure the heights of each one of these. Now, let's go ahead and let's do the part B. So part B for question 1. What was it? P of, okay. So part 1 is asking, what's the probability of getting exactly 3 correct? Well, that's going to be right there. 0.0512. So you got basically a 5% chance of getting 3 correct. Okay? Now, part 2 says, what's the probability of getting more than 3 correct? So let's see, is it more than 3? Nope, I already screwed this one up. Probability of getting less than 3 correct. So if you think about less than 3, that would be the probability of 0 plus the probability of 1 plus the probability of 2. Another way to look at this is if you're thinking about it less than 3, here are all the probabilities less than 3. So what you would have to do is add each one of these up. So if I do that real fast, I got 0.32768. Let me just write it out here. I think that's always helpful. So it's going to be 0.32768 plus 0.4096 plus 0.2048. And when you do all that correctly, we're going to get 0.94208. So if you think about what this problem is really asking, it's what's the probability that you're going to get at least, or I'm sorry, less than 3 correct? Well, chances are pretty high that you're not going to guess 3 questions. So 0.94208. So the next 2 questions, what I'm trying to get you to do is trying to think about what do these words mean? So when it says the probability of getting at most 2 correct. So the probability of getting at most 2. Well, if you think about probability of getting at most 2, then that's going to be equal to the probability of getting 0 plus the probability of getting 1 plus the probability of getting 2. So it's the same exact question as what we just did. It's just I asked it 2 different ways. If you think about it, if x is less than 3, then that means you're getting at most 2. So this is going to equal 0.94208. And then the fourth question here, probability of getting none of them correct. Well, the probability of getting none is equal to the probability that you get 0 correct. So that's going to be 0.32768. Okay? And that's how this works. It's actually not that difficult. Now, there are other ways that we can go about generating these numbers here in this binomial probability distribution table that we did. All right? And what I'm talking about here is this big thing right here, okay? We could cheat a little bit. And what I mean by cheating is there are graphs, there are tables, there are all these other things, and you have this very special tool that's available to you called the Statistical Analysis Learning Tool. And if you come over to the distribution calculators, because we're talking about probability distributions, notice that when you click on it, it gives you this normal distribution here. You could tell that it's normal on the left-hand side. All right, it says normal distribution. All right, see if I can zoom in here a little bit if it'll let me. There we go. Oh, that looks really bad. I don't like that. Never mind. All right, what we're going to do is we're going to click on this drop-down arrow, and you're going to see, oh, look at that number 2. It's a binomial distribution. So go ahead and click on binomial distribution. Now you have options. Fixed number of trials, probability of success, and then down here you have P of X is less than or equal to a certain value. So what we're going to do is we're going to go ahead and do our problems, and we're going to do the exact same ones all over again. So fixed number of trials, you're guessing on 5 questions. So we change this to a 5. The probability of success, well, you got a 0.2 chance of guessing the first question correct. Because remember, it's 1 out of 5. 1 divided by 5 is 0.2. So now, if we go back to our notes, what is the probability of getting exactly 3 correct? Now, we already found exactly 3 should be 0.0512. So if I go back to SALT, notice on the right-hand side, I got options. And one of them says, well, they say left tail, right tail, both tails, between and equal. Well, let's go equal. Now, look at the probability. It changed that inequality symbol to an equal symbol. And we want the probability of it getting exactly 3 correct. So I just move that up to 3. And notice here it says 0.0512, which is exactly what we expect. So the probability of getting exactly 3 correct, 0.512. Now, the next question was guessing at least, or I'm sorry, not at least, at most 3, or at most 2, or another way to say that is less than 3 questions. So less than 3 means 0, 1, and 2 questions correctly. So we're going to go back over to here. We're going to click on left tail. And then we have to move this down to 2. Because remember, we want probability of 0 plus the probability of 1 plus the probability of 2. Notice that our graph here is all highlighted, okay? And we come up with 0.94208. And if we go back to our notes, there it is right there, 0.94028. Now, question 3 was the exact same, but now let's look at question 4, which is the probability of getting none. So the probability of getting none is exactly 0. So equals, and then we're going to change this to the number 0. And the number 0, probability of getting none of them correct is actually pretty high. It's 0.32768. That is how this works, okay? So I hope this made sense. Okay, so now that you kind of see how the example works, we're just going to finish out the notes here. And the last part here is not going to be too difficult. It's just a matter of just using formulas. So if we have a binomial probability distribution, the mean is going to be n times p, which is the probability of success. Our variance is going to be n times p times q. And then the standard deviation will just be the square root of that. So if we use that previous example here, mu is going to be the average number of questions I would expect to get correct. Well, we have 5 questions with a probability of success of 0.2. So if I take 5 times 0.2, I would expect to get 1 question correct, which if we go back to that example, if you look at the table, that 0.4096, in fact, we can go back, I guess, to using salt here. Let me just click on salt real quick. So 5 questions, 0.2 success. When we go ahead and let me just click on equals. When we look, notice we go from 0.32768 to 0.4096, which is a higher number. And then as we increase the questions, our probability decreases. We can also verify that just by looking at the graph here. The highest peak is going to be 1 question, which is what we would expect to find. We would expect to get hopefully 1 question correct when guessing. Okay? Now, the variance will be 5 times 0.2 times 0.8. So our variance is going to equal 5 times 0.2 times 0.8. That's going to be 0.8 with our standard population deviation, which is just the square root of 0.8, is 0.894. And since we're talking about discrete problems here, I would just round that to the nearest whole number 1. And the reason why I'm doing that is because the last thing we're going to talk about here is our range rule of thumb. Remember, significant values are always going to, not significant values will always be in between 2 deviations away from the mean. Anything outside is going to be not significant. So if I use this information, 1 for my mean and 1 for my deviation, then what I'm expecting to find, mu plus or minus 2 deviations would be 1 plus or minus 2 times 1. So our normal values would range in between, well, let's see here. 1 minus 2 is going to be -1. And then 1 plus 2 is 3. Okay? So 1 minus 2, like I said, is -1. And then 1 plus 2 is 3. However, we're not guessing on -1 questions. So I would erase this and put a 0 for it to make sense. In other words, we would expect to find normal guessing between 0 and 3 questions correct. Anything outside of that, I would be suspicious. So if somebody had 5 questions and they guessed on all 5, the first thing I would say is, are they cheating? Because that is not what I would expect to find. That's not normal. Now, we could maybe go back to the student and notice that the student did not cheat at all. They just got extremely lucky, which is significant. You got really lucky. That's big time significant. Okay? So I got one more little example here at the very end, and it's kind of just going over how to use the range rule of thumb and everything. So let's do this example real fast. It's football season. I'm a huge sports fan, so I figured let's go ahead and use this. So using data collected about winning NFL overtime games, there's 460 games where the data has been collected. We want to find the mean and the standard deviation for the number of wins in groups of 460 games. Also, find the values that separate significantly low and significantly high values. Lastly, is the result if 252 overtime wins in 460 games. Unusual. So we got 3 questions here. So part A, n equals 460. Now, when you think about a game, you either win it or you lose it. So the probability of success is going to be 0.5. Probability of failure is going to be 0.5 again. So mu equals n times p. So that's going to be 460 times 0.5, or 230 games. Now, for part B, let's go ahead and let's find that range. All right. So mu plus or minus 2 standard deviations away from the mean. So our lower value is going to be 230 minus 2 times. Oh, we need our standard deviation. I didn't even calculate that. My bad. Sigma equals the square root of n times p times q. So that's going to be sigma equals the square root of 460 times 0.5 times 0.5. Sigma equals 10.7. All right. So now we're cooking with fire. So for part B, 230 minus 2 times 10.7, comma. The upper range or the upper limit will be 230 plus 2 times 10.7. So when you go ahead and do the math, initially you're going to get 208.6 all the way up to 251.4. However, since these are actual games, you can't have 0.6 of a game. I'm just going to go ahead and just say this will be 209, and I'll round this one up to 252. When in doubt, round the number up. 0.4 means you're already in the game, so round it up. So part C. If 250 overtime wins has occurred in 460 games, is that unusual? Well, 252 games would not be unusual because it fits in the range. Now, if you didn't round those numbers, then it would be considered unusual. So there is an argument to be had there. There really is. A conversation must be had there. But if we're just looking at this in terms of just numbers and just kind of fitting our problem to what we're learning, I would say it's really not unusual, but 252 games is still a lot. So anyways, so that's going to be it for this section. Very small section, very small chapter, very short week. I hope you enjoy it. And chapter 6 is when we really start hammering all these different types of distributions and really looking at inferential statistics from like a 30,000 foot view. So I hope you enjoyed it, and I'll see you in the next one. Bye.